Okay. Hello everyone, and do you see my screen, by the way?
Yes,
Okay, with the
yes,
election
Professor.
numbers. Awesome. Yeah, started recording. All right. So yeah, welcome to the lecture number 7. This is one of the most important lecture in the course. And I mean, still very basic, but the ground for everything what we're gonna learn next. So the title is Bloch sphere, single qubit and two qubit gates, and golden two qubit circuit. But before I start this one, let me really quick remind ourselves about the content of lecture 6, the previous one. Right, so in the lecture number 6, we finalized our quantum mechanics postulates. So we discussed postulate number 9 and 10. The postulate number 9 describes the mixed state versus pure state, right? We say that in the most important, in the vast majority of important cases, we don't know something. We lack of full information about the system. That's why we need to bring this classical probability distribution. Like, for example, if I have a gas of molecules, the number of molecules is so large I can't keep track of all the single molecules there. So lack of information about coordinates, about velocities, about other things, energy. That's why this lack of classical information motivates us to use the density operator or density matrix. Right, this is the general formula for the density operator, which is composed of these outer products of the different quantum states. For example, this index I can be like some particular velocity in the distribution of velocity of molecules over velocities. Right, so this outer product basically corresponds to the to the quantum probability of finding the state of a particular quantum system, and then we multiply this probability with a classical probability pi. Pi is the classical probability of getting this particular molecule with this particular velocity from the ensemble of molecules. I'm saying molecules, but in fact it can be any ensemble of any quantum systems. It can be ensemble of qubits, ensemble of whatever atoms, quantum dots, etc. So we discussed the properties of the density operator. We say that the density operator is always Hermitian, and some other properties. And the last one particularly allows us to check if the state is pure, so we know everything about the quantum system, or mixed. We have lack of information about the system. We discussed the density matrix of a qubit of a general two-level system without dissipation, and then introduced the decay and dephasing, and say that decay and dephasing described by two important parameters, which are relaxation time and dephasing time. Okay, so again, if I excite my qubit, for example, from the ground state to the excited state, after a while, namely after t1, the system goes back, it relaxes to the initial state, right? And also, when I excite the system preserves the phase of the signal I used to excite it. And this, the system gets dephased. It loses the phase after the time, namely t star 2. And this is the dephasing time. These two parameters are important, and as we will see today, for example, if I go here in this IBM Quantum, which is open on my browser, I can click on any available quantum machine, right? For example, this one, IBM Sherbrooke, it gets 127 qubits, etc. Other parameters, but these T1, T2 parameters, the dephasing and the relaxation time, always indicated, and the T2 parameter, dephasing, is always less than T1. We will get back to this one later. We also discussed last week the postulate number 10, which is basically about the way we describe the composed systems. Let's say I have one quantum system which is described by state psi. Let me change this one to psi 1 and psi 2. Okay, psi 1, psi 2, and H1, H2 are the Hilbert spaces of corresponding systems. The composed system, when I combine the two quantum systems together, is described, or it lives now in the composed Hilbert space, which is formed by taking the tensor product of the two, H1 tensor product H2, and the corresponding state is also described by a vector, which is now tensor product of the two vectors. Right, so these are new basis vectors. So we take one qubit, which is two-dimensional Hilbert space, another qubit, again described by a two-dimensional Hilbert space, and also by two-dimensional vectors, right? Then combine them, and the resulting space is four-dimensional, 2 to the power of 2, four-dimensional, and the state now of this combined system is a four-dimensional state, and this four-dimensional space, of course, is described or represented by four basis vectors. So all them are presented here. We discuss how to compute all these tensor products, etc., using SymPy. I encourage you to watch the previous lecture video on YouTube to refresh your mind. And then we say that sometimes when I get a state like this, right, this is the most general state of a system of two qubits. Sometimes some of these coefficients can vanish. For example, this C01 and C10 turn to 0. In this case, my state became something like this: state 00 plus state 11. What is important about this state, or a state like this? It's important to notice that this is so-called non-separable state. Non-separable state means it cannot be presented by the product of two states of different quantum subsystems. Okay, you cannot find like a way how to compose this state 0, 0, 1, 1, multiplying the two states of two different qubits in this case. This is the concept of quantum entanglement, right? So this is a state is said to be entangled if you cannot represent this state as a product of two other states, in drastic contrast to a separable state like this one. So this state can be rewritten in this tensor form, right, in this tensor product form, and this form can be represented in this way. So I just take the tensor product of this superposition with state 1 and it returns me this state. So this is separable state. This state is non-separable. And for a system of two qubits, we have very important concept of Bell states. There are 4 Bell states, all of them shown here. It's just basically different composition of this 0011 or 0110 states. So you can check that these 4 states are non-separable. And for this reason it's called 100% or fully entangled states. Very important. Also, if I consider a state like this, and if I prepare my quantum system in a state like this and then measure it, so before measuring the system, I don't know in which state it is, but let's say I have 2 qubits, they share this Bell state, right? And then I measure 1 qubit in this pair, and let's say I get state 1. You know that I can get either 0 or 1 with 50% probability, which is defined by this coefficient squared. So let's say I get state 1. And if I know that the qubit was initially in this Bell state, then I conclude that the second qubit gets the state 1 as well. State 1, 2. Likewise, if I get state 0 from measuring the first qubit, I also immediately conclude that the second qubit was or is in the state 0. This means that measuring the first qubit affects the state of the second qubit, or it affects the result of measurement of the second qubit. This is the concept of shared randomness, and the point is that these qubits can be billions miles away from each other, and it still works like this. You measure 1 qubit and immediately affects the second qubit state or probability of getting some result from the second qubit. So this is not just like theoretical curiosity. It is now like very established experimental fact, and we use this concept in many applications, including cryptography and quantum computing. All right, we discussed quantum parallelism, saying that okay, 1 qubit is described by vectors of 2 components, 2 qubits is described by vectors of 4 components, and in general n qubits, fully coupled, described by a system of 2 to the power of n components. And if I, for example, have a system like a computer of 500 qubits, which is achievable today. Today we have a computer of 1000 qubits, but still, if we have a computer with 500 qubits, such a qubit would be described by a vector with 10 to the power of 150 components. Okay, so you even cannot build a classical computer to store such a big number. So this is such a number is so big. This state of such a quantum computer is so large, right? So you cannot even save this information using a classical supercomputer. Still, this is very easy to achieve in quantum computers. We will return to this point later. And yeah, so this is basically what we discussed in lecture number 6. And let us proceed with lecture number 7. So, since last lecture, I add the lectures from the previous semester, which I taught using handwriting in my using my tablet. Okay, so I also encourage you to read the lectures in this hide writing style format, because it provides more details and it provides more like step-by-step calculations and maybe alternative angle of vision on the same concept. Okay. All right, so as usual, let me start from cleaning all outputs and restart the kernel. Really quick. Yep. All right, so this is the lecture 6, this is the lecture 7. As usual, we import general libraries, and also I import SymPy quantum libraries because it's like very useful and handy for symbolic quantum computations. And also activate this multiple output. All right, so the first concept for today's class is Bloch sphere. So what is a Bloch sphere? Bloch sphere is a nice and useful tool to represent a general state of a single qubit system. Okay, so if I have a single qubit, I can represent the state of the single qubit using the Bloch sphere. Why Bloch sphere? So single qubit is given by the two-dimensional Hilbert space, right? So one might say that a two-dimensional picture would be enough to represent a state of a qubit. However, the amplitudes of a single qubit are complex valued, so we need the sphere, the object with dimension larger than 2. So in fact, we need a three-dimensional sphere. So how we represent a state of a single qubit using the sphere? So let us look at this general state of a qubit with generally C sub 0 and C sub 1 complex valued. Okay, and the difference in phase. So these two complex valued can be represented in exponential form using the Euler's formula, right? And there will be some phase difference between these two amplitudes. And I can always say that I assume that the coefficient C0 is a real valued. Okay, so I just change the phase, or the way I count the phase. So I start, or I assume that this coefficient is real valued, and then the phase factor of this coefficient c sub 1 will give me the phase difference between these two coefficients. So it's said here, I assume that c sub 0 is real valued and c sub 1 is some amplitude, capital sub 1, multiplied by this exponential function e to the power of I phi. Phi is the phase difference, also real valued. Okay, and of course these two coefficients are normalized according to the Born's rule, right? Because the absolute values of these coefficients provide the probability of finding each state in experiment. And taking into account this assumption, this can be rewritten in this form. Okay. At the same time, so I see that the square of one value plus square of another value gives me 1. So I can use this trigonometry relation, right? So when sine squared of any angle plus cosine square of the same angle is equal to 1, right? So I can write this in this form, and then what I need to take into account is the fact that this coefficient c sub 1 also takes the phase. So I conclude that I can write the c sub 0 as a cosine theta over 2 and c sub 1 as a sine theta over 2 multiplied by this phase factor here. And why theta over 2 rather than theta, it will be clear from the what's following. Alright, so this is the formula. It's complete analog to this one. So this is basically written the same, but in the form of spherical coordinates. Okay, this is the complex representation. This is the spherical coordinates representation. If I treat this theta and phi as angles of the in the spherical coordinate system. Okay, this how's it, azimuthal and oh, I don't remember the names. Anyways, always forgot. Of course, I can use the Python libraries to represent the Bloch spheres. There are two libraries that are particularly useful for that. For example, Qiskit, which we are gonna use the most. You can call this from Qiskit visualization, just import plot Bloch vector, and then in this function you just give the spherical coordinates. You indicate that these coordinates are spherical, and basically it. So this is the way you get a Bloch sphere. Okay, and also it nicely indicates that this upper pole is state 0, this south pole is state 1. So we're gonna confirm this in what follows, but this representation is the answer why angle theta over 2 rather than theta. So theta over 2 allows you to represent the state 0 and state 1 as the not orthogonal, but the opposite direction on the axis of the sphere, right? So the state 0 is the vector points upward, the state 1, it points downwards like this. And if I need to change the state, right, of this vector, I just assign different angle. So this is theta, this is phi. And if I change this angle theta, it changes the orientation of this arrow. Okay, so each point on the Bloch sphere represents a different state of a qubit. In other words, all possible states of a qubit are represented on the surface of this Bloch sphere. Okay. The radius of the Bloch sphere is 1, is unitary, because this 1 corresponds to the normalization factor, right? It is 100% certainty. Okay, so this is normalization because of the normalization. Another way to represent the state on a Bloch sphere, to use a Q-tip. We are not going to use Q-tip, especially in the introduction to quantum computers. Q-tip, I introduced this one in the first lecture. Basically, Q-tip is the greatest Python library for numerical quantum simulations, like simulating a real quantum system, like molecule atoms, or systems like quantum optics, etc. Yeah, so this is another way to call for Bloch sphere. Let us describe the important states on the Bloch sphere. So two states we already know. The state 0 is the north pole, state 1 is south pole. But let us confirm that. Let us check that. So if you recall the Euler's formula, right, we can rewrite this general state of a qubit shown here in the frame, the box, in this way, in this form, right? So I just substitute for this exponential function the cosine plus I sine over here. Okay, so where is the state 0 on the Bloch sphere? So this is state here, right? This is the so angle theta. First of all, angle theta is counted from the vertical axis, from the axis z, which is orthogonal to the axis x and y. Okay, and phi is angle that counts from the axis x counterclockwise. So the state 0, this north pole, is given by the angle theta 0, because cosine 0 is 1 and sine 0 is 0. So we get only state 0. So we confirm that this is really state 0. Likewise, for the state 1, the angle theta must be equal to pi, or pi radians. And angle phi doesn't matter, but we assume to be equal to 0 for in this case. So here I guess I plot this angle theta 0 phi 0. This is the state 0, and state theta pi phi 0 pi 0. This is the state. This is the state 1. Okay, so we know where are the state 0 and 1. So we have also other important states of a qubit, which are plus and minus state and the plus I and minus I states. So let us look at the plus minus states first. Plus I is given by this superposition with plus between, and minus state is given by the same superposition but minus between 0 and 1. Okay. So again, simple calculation using this formula above gives us these values for the theta and phi. Theta, it must be equal to pi over 2. Because if you substitute theta pi over 2 to this formula here, you will get cosine theta over 4 and sine theta over 4, right? So you will get 1 over square root of 2, or square root of 2 over 2. Right, so this is exactly the normalization factor here. And phi equal to 0 makes this exponential function equal to 1. And if phi is equal to minus or is equal to pi, e to the power of I pi is equal to minus 1. This is how you get minus here. Again, let us double check using the Bloch sphere representation. So for the theta pi over 2 and phi 0 and theta pi over 2 phi equal to pi, I get these two states. So plus state is a state of a qubit along axis x. The minus state points in the opposite direction. Okay, so this point on the Bloch sphere is a state plus. This opposite point on the Bloch sphere is the state minus. And what is left? I and minus I, or actually plus I, it doesn't really matter, plus I and minus I states. Again, simple calculations give us this theta and phi angles, and I plot them. Pi over 2, pi over 2, pi over 2, and minus pi over 2, or 3 half pi. Okay, these are the orientations of the vector. So this state on the Bloch sphere is state plus I. This is minus I state. Okay, so a summary. So state 0 and 1 located on the z-axis. States plus minus located on the x-axis, and plus I minus I located on the axis y. Okay. So having introduced this Bloch sphere, we transit to the concept of quantum gates and quantum circuits. But before going to the quantum gates, let us quickly remind or learn a little about the classical gates. I'm not a classical computer scientist. I recall I learned something from like this in my university 10 years ago or so. But the principle is very simple. Okay, so the principle is that okay, you have some elementary elements like transistors, like this electronic key or electronic switch, and combining several transistors, you can create a logical gate, a logic gate. So a logic gate, there are several logic gates, and using these logic gates, we can basically create a logic. We can create a circuit, a logic circuit that conducts some computation for us. Okay. For example, any electronic computer is based on this classic gates. And as an example, let us consider this NOT gate. Right, so NOT gate is simple NOT gate. Yes, over here. So it is one input, one output. One input, one output gate. So NOT gate, what it does, it basically flips the bit. Right, if I have 0 in input, it returns me 1 in output. If I get 1 input, it returns 0 in output. Very simple. The logic of a classical gate is described by truth table. Okay, so I just write the possible outputs for the given inputs in the form of a table. So truth table. Using just one input gate is not enough to build a classical computer, electronic computer. We must have two input gates. And one example is this XOR gate shown here. So this is XOR gate. This is a classical analog of one important quantum gate. That's why I bring it here. So XOR. XOR gets two inputs and one output. And the operation of this gate is as follows. So if I have, so say I have two inputs, input A and input B. Okay. So if input A is in state 0, then my gate just returns the state B in output. You see this output here is equal to input B. However, if I change the state of input to 1, the gate flips the input state. So if I have state 0 in my second input, it returns me 1 in output. And if I have 1 in the input, it returns me 0 in output. So it is controlled flip gate. If I have 0 in input A, it does nothing. It just returns me input B. If I have 1 in input A, it flips the state of input B in the output. Important point to notice here is the irreversibility of this gate. So this gate, in fact, is irreversible or not reversible. Why? Because to the same input, for example, input 0, I have two drastically different inputs. So for a given output, I have two possible inputs, and for 0 and the same for 1. So if I have state, if I measure state in output, I cannot say the state in input. Okay, so this is irreversible gate. For a classical computing, that's fine, unless your unless your classical computer gets too big, because there is a theorem that says that if you have irreversibility, it leads to heating. Okay, so your circuit of irreversible gates converts energy to heat. So basically, you lose a lot of useful energy, and at some point your computer must be based on reversible gates like Toffoli gate and so on. But in practice, you can build the classical logic using irreversible gates. And as an example, I just put this example of adder, right? So this circuit just adds to binary logic units or elements A and B, and it makes sum or it subtract the values. Anyway, so this is how it basically works for classical computing. So let us go to the quantum circuit now. In quantum circuit model, we have a system of quantum bits or qubits, and we control their state using quantum gates. One important or crucial requirement here is that all quantum gates must be reversible, which means they must be unitary. The quantum gates must be unitary or must be represented by unitary operators or unitary matrices. At this point, I encourage you to go to the earlier lectures to refresh your mind about these unitary operators. But essentially, unitary operator is an operator that, being multiplied by the same operator dagger, right? Hermitian conjugation. It is equal to identity matrix or identity operator. So physically, it means that if I do computation in one direction, it's equal to the computation in the reverse direction. Of course, in reality, all qubits and gates are dissipative. We have decay and dephasing, as we discussed last week. So, in reality, no qubits and no gates are unitary. But we have to strive for the perfect quantum computer would be based on perfectly unitary quantum gates. All right, so here is an example of a quantum circuit or a typical quantum circuit. So each line here represents a qubit, different qubit. In quantum computers, qubit is a physical object. It can be realized in different way. We will discuss this towards to the end of the course. So for now, it doesn't really matter what's the physical nature representation of the qubit. It can be assumed by some sort of a quantum transistor, whatever, like atom or something like that. So different physical objects. And then we manipulate with the qubits using the gates. So here in this picture we can find different quantum gates, and each box and these elements here, they represent different quantum gates. In this circuit we can also find layers. Okay, so for example, this is layer number 1, this would be layer number 2, this would be layer number 3, and so on. The number of these layers in the circuit gives us the circuit depth. Okay, so number of different layers. And here I put a very important note to basically to notice the difference between classical circuit and quantum circuit. So in classical circuit, each of these logic elements represent a physical object. Okay, it can be some sort of a bunch of transistors or other electronic components placed somewhere on the chip, on the circuit. And then these wires, these black lines, they represent physical wires that connect the classical logic elements, classical gates. In drastic contrast to quantum computing, where these gates, quantum gates, they are not, or typically they are not physical objects. These are some sort of stimuli or pulses that control the qubit. Okay, so the quantum circuit, quantum chip, is composed of a number of qubits. The qubits connected somehow to form some sort of topology, and this connection is required to achieve quantum entanglement. Okay, so we can entangle different qubits on a chip. But these lines here, they are not special. These are not wires. It is, in fact, time. So this is the flow of time. Okay, so each of these wires, not physical wires, these are time. And the operations in each layer represent the actions, the stimuli that we use to change the state of different qubits. This is the difference. So classical circuit is a special, meaning that these are elements like distributed in space over the circuit. Quantum circuit is temporal, meaning that all these quantum gates distributed in time, if you wish. And here I bring this topology of a quantum computer IBM Torino just as an example. So each of these circle here represent different qubit. Okay, and as you can see, some of these qubits are connected or coupled to three neighboring qubits, right? And yeah, so this is one of possible like topology of a quantum computer, and in this quantum computer we have 133 qubits. All right, so this is like physical distribution of qubits over the chip, but you cannot find gates in this circuit. There is no gates here. Gates are pulses that we send to change the state of each qubit. Okay, so that's important to understand. This line is not physical. This is the time. So if I run some sort of quantum algorithm, my algorithm starts from the leftmost layer and run to the rightmost layer. And here, as a last layer of the circuit, I always have a layer of detectors, the layer of measurement. I have to measure the circuit when the algorithm executed. Okay, do you guys have any questions at this point? Okay, I see. No. All right, so let us then proceed to the particular quantum gates. In quantum, we also have single input gates and multiple input gates. Okay, so let us start with single qubit gates. So single qubit gates, we start with Pauli gates. So you recall from earlier lectures we discussed this Pauli matrices. Pauli matrix X, Y, and Z. We calculated the eigenstates, eigenvalues. I presented all this in form of a table. I guess it was lecture number 5 or 4. The one when we discussed the spin. Right, so this Pauli matrices describe spin. In fact, these Pauli matrices also represent important single qubit quantum gates. And we start from X gate, Pauli matrix or Pauli gate X. Okay, so Pauli gate X, or simply X gate. X gate is represented by this rectangle with X inside, or more often by such a circle with plus inside. So for example, in this circuit I don't see X gates, but we see this control X gate we will discuss in what follows. So this basically represents the state, the gate X. So the state gate X is given by Pauli matrix X with element 0, 1, 1, 0. Okay, also shown here. And by direct multiplication of this gate by qubit 0 and qubit 1, we can confirm that this gate converts state 0 to the state 1 and state 1 to the state 0. Let us call for the Bloch sphere again, so we can nicely see what's going on here. Okay, so again, if I start from the state 0, my arrow points up, right? State 0 here, the north pole, and I act the X gate on this state. It returns me state 1, so it will flip the state to the state 1, which is pi here, numpy dot pi. So this would be the final state. At this point, I noticed that what actually happened is flipping of the qubit from 0 to 1, and it happened in a way that it rotates along the axis X. And we will see in what follows, the same holds for all Pauli matrices. The Pauli matrix X rotates the state along or around the axis x. Pauli matrix Y rotates the state around axis Y. In the would be clockwise direction, right? Clockwise direction. And for the general state of a qubit, alpha 0 plus beta 1, if I apply this state x, the gate x, it just changes state 0 to the state 1 and state 1 to the state 0. I can, so the beauty of this SimPy quantum library is that people realized all the necessary qubits in this library, and I can import all gates from this SimPy physics quantum library using this function. Okay, when I did so, I can call this x gate by writing x capital and parentheses and indicating the number of the qubit in the parentheses. So if I, as usual, create the qubit in the state 0, right? This is the qubit in state 0, likewise qubit in the state 1. So I start from qubit in the state 0, and I act the gate x on this qubit and just run it. So this is the output in symbolic form. By default, it doesn't compute the result. Okay, in order to ask SimPy to compute the result, I write q apply and put this operation in parentheses. Apply, and the result is state 1, as expected. Likewise, for the state 1, for the qubit in state 1 initially, I get state 0. Okay, so this number in parentheses indicates the number of the qubit in the circuit. Okay, so for example, if I put 1 here, which is second qubit, you remember in Python, counts starts from 0. So 0 means first qubit, 1 means second qubit, and if I run it, I will get error because I have no second qubit in my simple circuit. Okay, so computational error. But I can add another qubit, just writing another 0 here or 1. Okay, so this is the state of 2-qubit system, state 0, 0. And I have 4 states like this, 0, 0, 0, 1, 1, 0, 1, 1. And now if I apply my x gate to the second qubit in my circuit, I indeed get the state flip of the second qubit only. Okay, in order to flip the state of both, I need to apply this gate x to the first qubit and to the second qubit as well. And it returns me spin or state flip for both qubits. Initially they were in state 0 and 0. After it gets state 1 and 1. And likewise I can continue for a larger number of qubits. For example, this one contains 5 qubits, right? And then I can do this spin flip for each of these of these qubits. And we discussed this nice function represent. It represents the state in a vectoral form, right? So if I like start from this initial state of the qubit, which is state 1, 0. After application of this X gate to this qubit, I get state 1, 0, 1. And likewise, for example, for this one, let me. Right, so this is the this is the state 1, 1, because I apply this X gate twice. First to the second qubit and to the second qubit, and now I can represent this state in the matrix form, and this is the result. Very useful. Another useful tool I want to share with you is so-called Kirk. Okay, so Quirk or Kirk. This is a online like a website. So you just run this link and you get to this website with many elements around. We will learn about the most of them in this course. By default, the circuit gets 2 qubits, the first one, the second one, okay, and by dragging the elements, like for example, we see this Pauli X gate here, right? This X Pauli gate here. I can apply these gates to the qubits, and dragging more creates other qubits below the upper ones. Right? More and more. The largest number, the maximum number of qubits the system allows to use is 16, 1/6. Also, this circuit contains Bloch sphere representation. You just drag the Bloch sphere here, okay? And for example, if this Bloch sphere measures the state or indicates the state of the circuit on the left side from the Bloch sphere. For example, this is the state 0, this is the state 1, this is the state plus, state minus, plus I, and minus I. Okay. And for example, if I start from state 0, then apply Pauli X gate, we see that this gate flips the state of the qubit as indicated on the Bloch sphere. Okay. And for example, I can put another Bloch sphere. So this Bloch sphere indicates initial state. This Bloch sphere indicates the final state after this X gate. So here I put a summary of application of X gate on a state 0, state 1, state plus, and state plus I. So we see that since X gate rotates the state around the axis X, which is this axis in orthogonal to the vectoral to the axis Z, to the vertical direction, right? It rotates the state by angle pi radians, and we get from 0 we get state 1. Here, likewise, from the state 1, we rotate to the state 0 plus state, or plus I. Let's start from plus I. So again, it rotates by a factor of pi, and I get minus I. This is minus I. However, if the state was initially parallel to the axis x, like state plus, it doesn't change the state because no rotation of this state around the axis x, right? Because this is just a point. We cannot rotate the point on the axis x. Yeah, and the maximum number of qubits is 16, and if I calculate what's the number of amplitudes it corresponds to, it's just 6 times e to the power of 4. So roughly 100,000 amplitudes. The number looks big, but it is a small number. So this Kirk is a nice system, but not for simulating a quantum computer. It is rather for learning applications. So just for learning. Alright, so having said all this, we transit to another gate, which is Y gate, or Pauli Y gate. It is indicated by this rectangle with capital Y in it. It is represented by Pauli Y matrix, 0 minus I 0. And by direct multiplication of this matrix by state 0, we can confirm that we get I times state 1. Likewise, if you start from state 1, we get minus I state 0. Using SymPy quantum, we can confirm this result. Right, so I start from qubit 0, multiply by gate Y, and ask to compute the result. The result is I times state 1. And likewise for the qubit 1. Again, the number in parentheses indicates the position, the number of the qubit in the circuit. In this case, it is qubit 1. If I would have more qubits in my circuit, this could be 1, 2, and so on. Using Kirk, again, I put a summary of action of this gate Y on the states 0, 1, plus and plus I. This is the result. Again, the main point to notice here is that gate Y rotates the state on the Bloch sphere around axis Y clockwise by angle of pi radians. Okay, and of course it can change phase. So gate Y also changes the phase. So this I here corresponds to change of phase. Sometimes this change of phase is important. Okay, so here I create state plus and state minus to check what's the result of action of this Y gate on state plus and state minus. Plus state, minus state. Okay, so the result is so if I start from state plus, here the result is state minus. I take minus I, and it's gonna be state minus. In good agreement with this picture. If I start from state plus, it ends on the state minus. And if I start on state minus, I get state plus in the result. So next, the Z gate. Again, Z gate is a Pauli Z gate represented by Pauli Z matrix. It is rotation of state around axis Z by pi radians. And this is the, to confirm these formulas. So since this is rotation around Z, it leaves unchanged state 0 and in state 1 with change of state 1 the sign, also the phase, right? And and this is the summary from Kirk about the state, about this gate Z. There are the next very important gate, and actually like one of the most important gates for the following, is so-called Hadamard gate. So Hadamard gate is represented by a rectangle with capital H in it. H stands for Hadamard, right? And this gate is represented by this Hadamard matrix: 1 over square root of 2, 1, 1, 1, minus 1. So the important feature of this gate is that the gate creates superposition. Okay, so if you have a qubit in state 0, the gate creates the state plus, which is perfect balanced superposition of state 0 and 1. Likewise, if you start from state 1, it creates a superposition of anti-superposition, state 0 minus state 1, okay, which is essentially state minus. So Hadamard gate creates superposition. We will see that this is very important feature, and the vast majority of quantum circuits have this Hadamard gates as a very first layer in the circuit. Like here, for example, here the circuit contains this first layer of two Hadamard gates, here and here, which creates the superposition of the 0 qubit, which is first qubit, to the state plus 0 plus 1, and this gate, this qubit, also will be in superposition of two states. Hadamard gate creates quantum superposition. In SymPy quantum, Hadamard gate is indicated by H, again with parentheses, with the number of the position of the qubit in the circuit. And if I apply this Hadamard gate on the qubit in 0 or 1, I get these two states, plus state and minus state. And here is the summary from Kirk. Again, Hadamard gate, very important, must know. And the list concludes with, I guess, 3 so-called phase gates. Phase gates, they change the phase of the qubit, phase of the partial state of the qubit. The most general is P gate. Okay, P stands for phase, so easy to remember. So this P gate just multiplies the second term, the second, how to say, this partial state by a factor of e to the power of I phi. You see, so it changes the phase of the second term by a factor of phi. Okay, so if I apply this phase gate on a state 0, I get just 0, nothing happens. But if I apply in state 1, it returns me this state 1 multiplied by this phase factor. And if I apply this state on a general state psi, which is alpha 0 plus beta 1, I get this with changed phase of the second term, the second partial state of the qubit. How to say, the example or the another phase gate for a particular phase, namely pi over 2 phase, is named S gate. So this S gate is just P gate with phase pi over 2. So e to the power of I pi over 2 is equal to I, right? That's why we have this I here. And the same logic holds here up to, this replacement of phase by I, phase factor by I factor. Okay, so this is the change of phase by a factor of pi over 2. T gate, likewise, I guess here, yes, in SimPy quantum we have phase gate, which is S gate in this library, and we confirm these two formulas here using this code: state 0, state 1. Finally, T gate. T gate is another phase gate with a particular phase of pi over 4. Okay, and this is the graphic representation. This is the matrix. Again, you just replace pi of phi by pi over 4, and it just changes the phase by pi over 4. And in SimPy we get this T gate. This is the result. Very good. So this is it about single qubit gates. Do you have any questions about this part? While drinking some water.
No, Professor.
Very good. Okay, so 2-qubit gates. As I said, like classical computers, where we need not only single input gate, we need also 2 input gates. In quantum, we also require 2 input gates to build a quantum logic, like quantum algorithms. In quantum, all 2 input gates must have 2 outputs. 2 inputs must have 2 outputs, because all the gates must be reversible, unitary. Unitary is synonym for reversibility. The most important 2-qubit gate is called C0 gate. It is denoted this way. So it applies to 2 qubits, qubit 1, qubit 2, right? This upper and lower. This black dot indicates the control control qubit. Okay, so this control qubit will control the state of the lower, which is target. So this circle with plus in it is a target qubit. This black one is control qubit. Okay, the state of the target qubit depends on the state of control qubit. Very similar to what we said about XOR gate. Excuse me. So here, similarly, the state of the output depends on the state of the input A. If input A is 0, it just returns input B to the output, you see. If input A is 1, it flips, it inverts the input B. So 0 becomes 1, 1 becomes 0. Similarly here, this gate controls the state of the control qubit, or of the target qubit, by the state of control qubit. The matrix of this CNOT gate is given here. So since this is 2-qubit gate, it must be represented by 4x4 matrix. You remember this the tensor product of 2x2 matrices. One can notice here 4 submatrices, right? This, if you put this vertical and horizontal diagonals, these 4 elements 1 0 0 1 is just identity matrix, and this one 0 1 1 0 is exactly X gate, X Pauli gate presented here. 0 1 1 0. Okay, so this matrix nicely represents that if your state, if the state of the control qubit is 1, you use this upper leftmost submatrix, which returns just the initial state. If the state of the control qubit is 1, it flips the state, the 0 state. It flips the state. So here is the logic. C0 is another, it's just the name of the qubit. Sometimes we use C0, sometimes we use CX, because this is control X, right? Which works as X qubit, but controlled by the state of another qubit. Okay, so when we apply CNOT gate on a composition of 2 qubits, in this form, this first qubit here, this one, is a control qubit. The second one is target qubit. Okay, so if control qubit is 0, I do nothing, or this gate does nothing. It takes 0 for the target and returns 0, state 1 and returns 1. So it's trivial. However, if the state of control qubit is 1, it flips the state of the target. It was 0, became 1. It was 1, it flips to 0. And in SymPy quantum, we have the CNOT gate as a CNOT gate, or alternatively, we can just write CNOT. It's the same way, doing the same thing. 0, 0, 0, 1, 1, 0, 1, 1. In this case, this gate gets two indices. The first one indicates the control, and the second one returns the target. Control and target. This way you indicate which one you apply your gate to. Okay, so this is important gate. I encourage you to practice this part. Practice with the order, control and target, with larger number of qubits, for example, and so on. But we transit to the control Z gate. This one is also important, and we will use this one when we will talk about these quantum algorithms. For example, this Grover algorithm uses this control Z gate. So we need to get ourselves familiar with. Again, this is the representation. There are two options here. Control Z. It is essentially Z gate, but controlled by another qubit. If the control qubit is 0, the gate does nothing. If it's 1, it basically applies the Z gate, which is in this case just changing of the phase of the state. So this is represented here. So if the control is 0, it returns the output, the input of the second qubit of the target. However, if the control is 1, it returns the same state, but changes the phase of this state 1. So basically, it's exactly operation of the gate Z, but controlled by the state of another qubit. Another 2-qubit gate is so-called swap gate, and it does exactly what its name means. It just swaps the state of 2 qubits. In circuitry, it's represented by this swap, right? So the state of the first one became state of the second, and state of the second becomes state of the first, or the element like this. This is the matrix of this gate, and this is the operation. So for 0, 0, 1, 1, it does nothing, obviously, but for this state 0, 1, it becomes 1, 0. For the state 1, 0, it becomes 0, 1. Swap of the state. And in SymPy quantum, again, we can call for this function, for this gate, using swap gate or swap with capital letters. This is the result. The result is completely basically the same. Sorry. Okay, so this is basically it about the quantum gates. We learned single qubit gates and 2-qubit gates. A few remarks about the quantum gates. So in classical computing, we know these theorems, like the theorem that says basically that in order to create a like general logic, we need a finite number of classical gates. I don't remember the number, maybe 4 or something. In quantum, we have a similar theorem, which basically says that for the general quantum logic, we need 3 single qubit gates and 1 2-qubit gates. In fact, even two single qubit gates and 1 2-qubit gate would be enough to create a general quantum logic. Okay, which means basically that this swap gates, for example, this Ctrl Z gate can be replaced by this C naught gate plus something else. Like, for example, this Ctrl Z gate in fact can be replaced by C naught plus 2 Hadamard gates. Okay, and so on. So these elements are reversible, and when we use, for example, this IBM Quantum, sometimes the program adapts or modifies the circuit in a in a way it can compute. Okay, so it modifies the circuit in a appropriate, to get it in an appropriate way. One could ask if we need like more qubit gates, like 3 qubit gates, 4 qubit gates. That's not necessarily. Again, any circuit with any number of qubits can be represented by single and 2 qubit gates. There is this Toffoli gate, the analog, the quantum analog to the classical Toffoli gate. And some of you maybe know that this like general logic, the general classic computer can be represented by the finite number of these Toffoli gates. Similar things holds here in quantum too. But again, it's not necessary for computing, because these Toffoli gates can be represented by a finite number of 2 qubit gates and plus some single qubit gates. Okay, so let us return to this picture here. And this circuit, we recognize these Hadamard gates here and here, Control X gate here, 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 and here. This one, so it indicates 2 qubit gate. This one, 1 qubit gate. This is T gate, right, which is phase gate. Another phase gate, some other Hadamard gates, and so on. Again, because of the unitarity of all these gates, if I run this circuit in the opposite direction, not from left to right, but from right to left, I will get exactly these initial states. Okay, so I can run the circuit in both directions. But this is only in theory, right? In theory, the gates must be unitary. In reality, of course, there is always some level of noise, errors, dephasing, and so on. But there is a like a benchmark, right? This test that I conduct to basically see how perfect my quantum circuit is. So I basically run the circuit from left to right, and then do the same from right to left, and compare the result. And this difference in the result basically indicates the imperfectness, right, of my quantum computer. Okay, so I have all these gates. How actually I can draw the circuits, right? In SymPy Quantum, that's easy. I use this circuit plot. I import the circuit plot. Okay, and as I import it, it allows me to basically draw the circuits. So let me first draw a circuit with empty circuit with a number of qubits to be equal to. It doesn't allow me. Can I? Yeah, I can just put some gate here. So this is the circuit that is composed by 2 qubits and one X gate. I can, for example, put Y gate here, applied to the first qubit. Important point to notice here is that it counts from bottom to top, right? So this is the first one, this is the second qubit, this is the third qubit, and so on. This is in drastic contrast to IBM Qiskit, for example. In that platform, the counting starts from top to bottom. This would be first, the second, the third. There is some discrepancy between different platforms, different approaches. Anyways, the result is always the same. Yeah, I can change the position of this gate, and if I want to bring another gate, for example, this one to the second, yeah. So you see this order of the gate corresponds to the different layer, right, in the circuit. Also, an important point is that the gates run from right to left. When I multiply this H, let me put this one, for example, 0, this is 1, it's gonna be 2. So I expect this H appear on the upmost qubit here. Yeah, exactly. So this is yeah, and of course, if I bring C0 with control, for example, 0 and target 1, yeah, so I get exactly this. So this control is 0, target is 1. I can, of course, flip it by changing it like this. So now this control is 1, target is 0, and so on. So this way I can draw any circuit of any number of qubits, even 16. Right, so I get this circuit of 16 qubits. The beauty of SymPy Quantum is also that, let's say I have this circuit here. I run it, so it's a circuit like this, okay? So now I want to compute what's the output. So for that I can use SymPy like directly. Okay, so I initiate the initial qubit state to all zeros. So this is 0, 0, 0, 0, 0, all states are 0, so all the qubits are in the 0 state, right? This is the qubit of the initial, oh, sorry, the state of the initial qubits in the initial time instant. And then I apply x qubit, y qubit, z qubit, and c naught as indicated over here. And what's the result, right? What's the result? The result of this is just this product without computation, because I didn't ask SymPy to compute the things. So if I put q apply to all this, it returns me the state, the final state after all these computations. Okay, so this is the state of the this is the state of all qubits in the final, basically, time moment. And if I want to know what's the state in the matrix form, I write represent in this state, and it returns me this state of the final vector of the final state. And the last point for today is this concept of golden 2-qubit circuit. Okay, so it is not settled terminology. Okay, so I heard this name some time ago in some lectures, and I prefer to use this one because it indicates the importance. Okay, so this is really a building block of something very important. So let us draw this golden 2-qubit circuit. So 2-qubit circuit contains 2 qubits, obviously, and it contains of Hadamard gate in the first qubit, and then this C0 gate with control first and target second. Let us compute the output state of this from this circuit, provided that the input state is in state 0, 0. So I write initial state, the state of the 0, 0, and then final state is initial state. Then I multiply this Hadamard gate and then C0 gate with 0 qubit control. First, the qubit 1 is target, and then I just print out the final state. Remarkably, the final state is the entangled state. This is the Bell state. This is 1 over square root of 2, state 0, 0 plus state 1, 1. Here I took this reminder from this lecture 6. So this is exactly the state here, this Bell state. As we discussed, Bell state is the most entangled quantum state, non-separable state that cannot be given by the product of two states of two subsystems. This is entangled states. And today we can easily create such a circuit with just two gates, Hadamard and C0, and this circuit will generate Bell states. So this golden 2-qubit circuit generates 100% entangled, perfectly entangled quantum states, Bell state. Very good. What if I start from state 0, 1? what would I get? I would get state 0, 0, minus 1, 1. This is the second Bell state. What if I start from state 1, 0? Surprisingly, I get state 0, 1, 1, 0, which is the third Bell state. And finally, what would I get starting from state 1, 1? Yes, I get the fourth Bell state. So Bell state, using this circuit, we can create all these four different Bell states. And if we recall that these states 0, 0, 0, 1, 1, 0, 1, 1 represent a basis in the four-dimensional Hilbert space of a system of 2 qubits, it means that I can change the basis to the Bell states and use Bell states as a new basis to describe any state of this system. Okay, so Bell states are also orthogonal. You can easily check that, and you will do this in your homework. And these orthogonal states can be used also to represent the things as a basis in four-dimensional Hilbert space. Yeah, and let me stop at this point. Or maybe just notice that if you have your Qiskit installed, you can draw the circuits also in Qiskit. This is what we're gonna use extensively in what follows. So this is just like the first encounter with, first meet with this Qiskit language. So Qiskit has been created by IBM, and they use this language for their quantum computing. And today Qiskit is, I guess, one of the most popular libraries for quantum computation. We will learn the syntaxes in what follows. I just say that, of course, we can create this Hadamard gate, Control X gate, as well as other gates in a similar way. And we can print these circuits. It will be like this. And if I need to change the circuit, for example, add another Hadamard gate like this, for example, or another A, X or Y, I can of course create more sophisticated quantum circuits. Yes, and the important point to observe here is the way the qubits are represented. So in Qiskit, the counting starts from 0 and then 1, 2, 3 and so on, from top to bottom. In contrast to SymPy quantum, where counting starts from bottom and goes to top. So this is why these circuits look different. So for example, in SymPy quantum, this circuit is exactly the same as this one here, except for the measure. I removed the measurement. Yeah, so this is exactly the same as this one, but flipped, right, upside down. All right, so this is the end. Thank you very much, and let me stop the recording and then we can discuss. Thank you.